Hello students, myself Rakhi Kumari, Assistant Professor in the Department of Electronics and Communication Engineering, ABS Engineering College, Ghaziabad, affiliated to Dr. APJ Abdul Kalam Technical University, Lucknow. Today in the lecture series of Microwave and Radar Engineering, we will go through Magnetron. As already we have discussed about the different types of microwave sources such as klystron, that is two cavity klystron, and the reflex klystron. In this series we are now going to start with the magnetron. So, what is magnetron? So, magnetron is a device which generates high power electronic wave and it is a self excited microwave oscillator. So, what is the difference between a klystron, which we have already discussed in the last lectures, and the magnetron? The first difference is it is a self excited oscillator. That means it will work, it will start oscillating even if no RF signal is applied to it. And the second difference between the klystron and the magnetron is that it is our crossed field. It is a crossed field device. And the reason that it is called as a cross field device because electric field and the magnetic field produced inside the magnetrons are perpendicular to each other. And if you can recall, in the klystron the electric field and magnetic field are not perpendicular to each other. So, these are the two basic difference between the klystron and the magnetron. The first one is it is a self excited microwave oscillator, and the second one that is a cross field device in which electric fields and magnetic field which are produced inside a magnetron, that is the tube, are perpendicular to each other and they cross each other. That is why it is also called as the cross field device. Now, the basic operating principle of a magnetron. The magnetron is a vacuum tube of high power having multiple cavity. If you are recalling the cavities are also used in the case of our klystron, that is the two cavity klystron as well as the reflex klystron. So, cavities which are used are basically the rentrant cavity. And if you can recall, in the two cavity klystron, the number of rentrant cavity is 2, and in the reflex klystron, the number of rentrant cavity is 1. But in the case of a magnetron, we will have a multiple cavity, and that is the reason it is also called as a cavity magnetron, because of the presence of anode in the resonant cavity of the tube. So, when we go through the construction part of the magnetron, then we will see how their anode is present in the resonant cavity of the tube. And since it has got a multiple cavities, that is more than 2. The operating principle of magnetron is such that when electron interact with the electric and magnetic field in the cavity, high power oscillation get generated. So, the principles are almost same, but there is a slight difference between the klystron and the magnetron working. The basic principle is that the electron interact with the electric and magnetic field, oscillation of very high power are used. So, one more difference arises here, that is the generation of signals is of very high power in the case of a magnetron as compared to the already discussed klystrons. Now, the construction of a magnetron. So, if you have a look at the construction of a magnetron, so let us look at a basic thing which we will discuss in detail in the anode. Cathode and anode are always the basic part of any microwave devices, microwave sources. So, this is the cathode, this is the center one, this is a cathode and it is responsible for generation of electron. Then second one is the outer cylindrical structure. This is the anode, and the radius of a cathode is A and the radius of a anode is B. So, you have to remember these points because these terms are going to be coming further in the lecture, that this center one is the cathode having a radius of A and the outer one is the our anode having a radius of a B, and this cathode is responsible for the generation of the electric field, and a high magnetic field structure is present, which are used to provide a magnetic field source of B naught, and here we can have the RF output, and this V naught is just used for the biasing of the circuit. So, this is the basic construction of a magnetron. Just go one by one. The cylindrical magnetron has a cylindrical cathode already seen by you, that is represented by having a radius of A of certain length and radius present at the center, which is present at the center, around which a cylindrical anode, the outer one. The cavities are present at the circumference of the anode at equal spacing. The next thing important, that is the cavities. If you are able to see these structures, these are the cavities and it is present at the outer structure of an anode. You are able to see this. These are form a part of, this is the anode, and here comes the cavities, here comes the our cavity. So, you can see that the cavities numbers are many in this structure also, 1, 2, 3, 4, 5, and in this way also. This is basically showing a 8 cavity magnetron. So, we are able to see the, and the all the cavities are at equal spacing, and the area which exists between the cathode and the anode of a tube is called the interaction space, because the electron interaction with the RF signals all working and all the generation of oscillation occurs in this region. So, this region plays a very important role. And next thing, there exists a phase difference of 180 degree between the adjacent cavities. Therefore, cavity will transfer their excitation from one cavity to another with a phase shift of 180 degree. That is why somewhere you are able to say that in the magnetron we have a pi mode. This term also exists in a case of a magnetron, and always you see in our books also that in magnetron there exists a pi mode. The reason for the existence of the pi mode is that the phase difference of 180 degree between the cavities, and the cavity, one cavity transfer their excitation to the another cavity with a phase shift of 180 degree. So, this is the reason that always we have a mentioning of pi mode in the case of magnetron. Now comes the working of a magnetron. So, as we have seen that there exists a cathode, there exists a anode, and in between there are cavities and the interaction space. So, first of all we divide the working of magnetron in the case of in two parts, when RF input is present and when the RF input is not present. So, first of all we will have the when RF input is not present. So, what will the, in this case also when the RF input is not present, we will discuss 3 to 4 cases, and in the case when RF input is present, then also we will discuss 3 cases. So, just start with when RF input is not present. So, when the RF input is not present, what will the cases exist? When the magnetic field is 0 or absent. The first case which exists, if the cathode is generating the electrons, then we already assume that electric field is existing. But what we are considering here, that magnetic field is not existing, that is E is existing, but B is not existing, that B is considered to be 0. And one more thing we have to know, that electric field provide a straight movement of electrons, and magnetic field provide the curvy movement, or we can say the movement of electron with having a arc. So, whenever we discussed about the here, we have to remember these 2 points. So, when the magnetic field is absent, then the electron emerging from the cathode. So, if we assume it as a cathode and the outer one of course anode, which is represented by the cylindrical cell. So, cathode, when the electron is emerging from the cathode, it moves towards the anode in a straight line. This is because the moving electron does not experience the effect of magnetic field and moved in a straight path. So, whenever we are having the electric field only, so it will have the straight path. So, from cathode to anode, electron will move in a straight path. So, whenever we discuss the magnetron working in your examination also and in your lectures also, you always try to show with the diagram all where a magnetic field is present. So, now the second case arises when, of course, this cathode and the anode is existing. I am representing cathode with a C and anode with a A. In case the magnetic field exists inside the now here electric field is existing, magnetic field also exists, but in a small. So, what will happen? This electron which is coming from the cathode to and going to the, it will experience a certain deviation from the straight path, and this is due to the presence of magnetic field. Since the magnetic field strength is small, so we are experiencing a little deviation, and if we keep on increasing the magnetic field intensity, what will happen? The intensity of deviation keeps on increasing. So, you can experience the deviation, it keeps on increasing if we keeps on increasing the strength of the magnetic field, and this is explained in the case third. In case when the magnetic field is further increased, then electron emerging from the cathode get highly deflected by the magnetic field, and one condition arises that when it will graze, it will touch. Graze means it will touch and move. This is called the condition of grazing, and this grazing condition is called as the, in this case, anode current is 0 because it is moving away from the anode after grazing the anode circle. So, the value of the magnetic field that causes the anode current to become 0 is known as the critical magnetic field, which is represented by BC, and this is a very important part, and we have always comes in a question, what is meant by the critical magnetic field. So, in that case you have to explain with a diagram also and with theory also that when the magnetic field reach to such an extent that it will graze the anode, and in that case the anode current is just touches the value of 0, and this is called the critical magnetic field. The magnetic field value at this point is given as critical magnetic field, and it is represented by BC. In this further in this lecture only we will discuss about the value of BC also. Now, the fourth case, if the magnetic field value is increased beyond the critical magnetic field, the electron will bounce back to the cathode itself without reaching the anode. So, we will have the case 4 also here, anode and the cathode. If the magnetic field value B is increased beyond the critical magnetic field value, that is more than the BC, then it will return back to the without reaching the anode, that means it will not touch the anode circle. So, in that what is happening in that case, our emitted electron from the cathode back to itself is known as the back heating, and what will it do to the anode? Anode will start heating, that is why it is called as the back heating. To avoid this, the electric supply provided to the cathode must be cut off after oscillation has been set up. So, the back heating is always dangerous for any type of instrument. So, we have to avoid it. So, oscillation has already been started. So, we have to cut the electric supply so as to avoid the back heating of a device. So, this is the case when the RF input is not present. Now, the case when RF input is present. In case an active RF input is provided to the anode of the magnetron, then oscillation is set up, of course, in the interaction space of the magnetron. So, when an electron is emitted from the cathode to anode, then it transfers energy in order to oscillate, same as in the case of a klystron. Electron transfer its energy to the RF signal so as to provide the amplification and the oscillation. Such electrons which transfer their energy, remember the point is important here, the electron which transfer their energy to the RF signal in order to oscillate, such electrons are called favored electrons. And in this condition, electron will have a low velocity and will take a considerably high amount of time to reach from cathode to anode. So, we have two types of electrons coming in the case of this, that is RF field is present or not, favored or unfavored. Favored electrons are responsible for the oscillation, and in this favored electrons always has a less velocity and it takes a high amount of time to reach from cathode to anode, and only that electron which come from the cathode and reaches the anode can give rise to oscillations. So, that is why it is called as the favored electron. The second condition arises in the presence of the RF input. In this case, what will happen? The emitted electron from the cathode while travelling takes energy from the oscillation. Now, the condition for unfavored electron comes. The electron which is coming from the cathode and moving towards the anode takes the energy from the oscillation, and what will happen? Its velocity increases, and if its velocity increases, what will happen? It, despite reaching the anode, it bounces back to the cathode again, and that electrons are called as the unfavored electron. So, now you are clearly understand the difference between the favored and the unfavored. The electron which have low velocity, which give rise to oscillation, moves from cathode to anode, and it takes much time because it has got a low velocity. They are called as the favored electrons, and the electrons which takes up the energy from the oscillation, they will have a high energy, and since presence of the high energy, it bounces back to the cathode. It is emitting from the cathode and it bounces back to the cathode, and what is happening here? That is back heating, and the electron in that case is called as the unfavored electron, but try to remember this is the case when RF input is present. Now, the third case, when the RF input is further increased, the electron emitted while travelling increases its velocity in order to catch up the electron which is already emitted, that is the electron which is emitting next. We can say the first electron is favored, second electron is unfavored, and the third electron which is emitted tries to reach the velocity of the first, want to reach the destination at the same time at which the first reaches the anode. So, what it has to do? It has to increase its velocity. So, increases velocity to catch up the electron emitted earlier, that is the first one comparatively, which is comparatively at the lower velocity than at this one. So, all this electron that do not take energy from the oscillations, this electron is also considered that it will not take energy from the oscillations. So, what will it do? It is also called as the favored electron. So, the main difference between the favored and unfavored, that it will take energy from the oscillation or it will not take the energy from the oscillation, and this favored electrons from electron bunch or electron cloud reaches anode from the cathode. The formation of electron bunch inside the tube is known as the phase focusing effect. So, this is also important term. So, how will you define the phase focusing term? That there is a cathode, there is a anode, and RF input is present. So, some electron will move from cathode to anode and some electron will not move from cathode to anode, it bounces back, but the further electron which is emitted will also reach the cathode with the same at the same time, but with the increased velocity, and the formation of bunch of electrons occurs, and this is called the phase focusing effect. So, due to this, the orbit of the electron get confined into spokes. This spoke rotate according to some fractional value of the electron emitted by the cathode, क्योंकि fractional value why भी, because some are favored and some are unfavored until it reaches anode while delivering their energy to the oscillator, and the movement of this favored electron inside the cathode inside the tube enhances the field existing inside the gap in a cavity. This leads to sustained oscillation inside the magnetron, they are providing high power at the output. So, the favored electron keeps on moving inside the interaction space between the cathode and the anode, and this gives rise to high power at the output. So, this is the same the movement electron path, which is for the when the magnetic field is increased beyond the magnetic cutoff. Now, comes the frequency pushing and the frequency pulling. The variation in the oscillation frequency of magnetron give rise to the term frequency pushing and the frequency pulling. These are the required for the definition purpose only. The variation in the oscillating frequency of the magnetron give rise to frequency pushing and the pulling. When the voltage applied at the anode of the magnetron is varied, then this causes the variation. When the voltage applied, that is what we are voltage applied. If you are able to see, this is the voltage applied. So, when the voltage applied at the anode of the magnetron is varied, this causes the variation of the velocity of the electrons moving from cathode to anode, because we have seen in the when RF input is present at electron velocity keeps on increasing. So, this resulted in the changes the frequency of oscillation, and therefore, we can say the resonant frequency of the magnetron shows variation due to change in the anode voltage, and this is called as the frequency pushing. Now, the frequency pulling, the change in the resonant frequency is sometime as a result of change in the load impedance of the magnetron, and the load impedance varies when the change is purely resistive or reactive. The frequency variation in this case is called as the frequency pulling. So, when we define the frequency pushing and the frequency pulling in the single term, when the our anode voltage is responsible for the change in the frequency or the resonant frequency of the magnetron, that is called the frequency pushing, and when the load impedance of the magnetron is responsible for the change in the frequency, then it is called as the frequency pulling. Now, comes the case of a Hull cutoff voltage equation. It is named after the scientist who first give the equation, the value of the BC, for which after increasing that, if we increase the magnetic field value beyond BC, what will happen? Electron emitting from the cathode does not reach our anode and it bounces back to the cathode. So, this plays a very important role. So, we have not to increase the magnetic field value beyond this. So, this value has to be calculated for each and every magnetron. So, equation of the electron motion in the magnetron is given by this expression, where B naught is equal to Bz assumed in the positive direction. Now, when we write it in the arrangement, rearrange this equation, how we will write? D by dt of r square, we are taking the d by dt in the inner side, r square d phi by dt, and this r comes this way. So, E by m Bz into r dr by dt, and we know omega c is equal to E by m Bz, that is called the cyclotron angular frequency. So, we are changing this E by m Bz with a omega c, and this r square comes to the this side and it is represented by r square, and the denominator we are taking the 2. Now, when we integrate that expression, we have r square d phi by dt 1 by 2 omega c r square plus constant, and now we have to calculate this constant. For that condition, we are taking the case when r is equal to a, and if I remember, r is equal to a for the cathode. Cathode radius is a, radius of the cathode cylinder, and in this case d phi by dt is equal to 0. So, what we will going to do? We are substituting R is equal to A, that means A square d phi by dt is equal to 1 by 2 omega c R square. So, we are also saying that in the case of A, R is equal to A, d phi d by dt is equal to 0. So, what is the constant value? It is exact the negative of, because this whole term is equal to 0. So, constant value is equal to minus of half omega c A square, because R is replaced with A. Now, we substitute the value in this. So, we are having this. Now, when the magnetic field comes into existence, since the magnetic field does not work on the electron, the case when magnetic field does not, in that case movement of electron, that is kinetic energy, is equal to the electric field, because no magnetic field is applied, the whole movement of electron is dependent upon the electric field. So, half mv square is equal to ev, this is the expression for electric field, and in this case when R is equal to B, where B is the radius of the center of the cathode to the edge of the anode, and in this case when V is equal to V naught and dr by dt is equal to 0. So, on substituting, what we are getting? We are getting this value, because what we are having, d by dt 1 by omega c 1 by 2 omega c 1 minus AC. Now, rearranging it, we have the value of this. Now, we substitute the value of d phi by dt in the B square, this expression, and on this we are getting this value. Though the electron will acquire a tangential as well as radial velocity, whether the electron will just graze the anode and return towards the cathode depends upon the relative magnitude of V naught and B naught. Ki electron will graze the boundary of the anode or it will return back, depends upon the value of V naught and B naught. So, the value at this particular case is given by the magnetic cutoff, that is BOC, and it is given by this, and if we want to continue with our value of V, so we just rearrange it and we have that value. In this case, this BOC is represented by B naught. So, this is a derivation part of the Hull cutoff voltage equation and the magnetic field. Now comes the cyclotron angular frequency. Since the magnetic field is normal to the motion of electron that travels in a cycloidal path, the outward centrifugal force is equal to this one, and the cyclotron cyclotron angular frequency of the circular motion of the electron is then given by V upon R. So, you can have this value just by rearranging this equation. Now comes the advantage and disadvantage of the magnetron. Magnetron is a highly efficient device used for generation of the high power microwave signal. The use of magnetron in radar can produce radar system of better quality for tracking purpose, and it is usually small in size, thus less bulky. The disadvantage, it is quite expensive. Despite producing a wide range of frequency, there exists a drawback in controllability of the generated frequency. Third one, it offers average power of around 1 to 2 kilowatt, and magnetrons are very noisy. And these are the application. So, major application lies in the pulse radar system and used as a heating appliances like microwave ovens, and tunable magnetrons find their application in the sweep oscillation, where we can. So, what we mean by the tunable magnetron, where we can have a control over the frequency. So, here comes the end of the topic of the magnetron. We will have the other microwave device in the next lecture. Thank you.